This is a production of Cornell University.
All right, thanks, Jeff. I'm happy to be here and kick off the seminar series. This is a little different from what I'm doing now, but it's something that I'm very enthusiastic about. So hopefully I can convey some of the interesting things that I learned over the course of an 8-year stint in BEE. So I'm going to talk about ways that the atmosphere and the landscape combine or interact to produce flash floods in the Northeast US. So the structure of my talk will just be some background on flash floods, and then describe my study methods, and then talk about the variability in what's happening in the atmosphere, what's happening in the landscape, and then I define some runoff types that help us sort of address how flash floods work here in the Northeast. And then a separate study that I'll talk about just briefly is how people influence the prevalence of flash floods, and then tell you my conclusions. So the definition of a flood is fairly intuitive for most people. It's where water is and that it usually isn't. So we think of floods like in the Midwest, where acres and acres of cropland are flooded and it lasts for months and months. And we can talk about floods, river floods, as water where we don't want it to be. It's flooding our cities and our homes and our crops. And hydrologists talk about floods in different ways, but the definition that I'm using is the Weather Service definition, which is of a flash flood, which is a flood that occurs within 6 hours of the onset of whatever caused the flood. So all of the floods I'm talking about is precipitation, but it could also be something like snow melt or dam break. So the flash floods are different from river floods because they're quick, like the name sounds. They happen quickly, and the inundation might not last very long, and it's difficult to pin down where and when the flood happened, and how long, how much area it covers and things like that. These are things that are more routinely characterized for river floods. It's harder to do for flash floods. And since flash floods are generally reported by people, not by gauges or remote sensing, then there's a bias in where they're reported. So they're only reported if someone notices and calls and says, there was a flash flood here. So so I'll get into a little more in a bit about how I deal with these challenges of detecting and then delineating where flash floods happen. So the motivation for studying flash floods is fairly simple. Flash floods cost lives and money. In the Northeast, we see damages in the millions of dollars every year, and unfortunately people die almost every year in the Northeast as a result of flash floods, despite the public awareness campaign of the National Weather Service that you may have seen the signs, turn around, don't drown. It's a significant cause of death in terms of weather-related deaths throughout the U.S., but I'm focusing on the Northeast. So what causes flash floods? What we already know before I got started on my work, we know that in the atmosphere we need sufficient water and energy to produce heavy rainfall. So heavy rainfall could mean either intense rainfall for a short period of time. It could mean a longer period of time with less intense rainfall that still results in a high volume of water. In the landscape, we know that higher slopes lead to more flash floods. We know that certain soil properties that I'll get into more detail make a landscape more susceptible to flooding. And when we pave or in other ways make land area impervious, that makes it so the water has nowhere to go. So if we don't do a good job in routing that water away from homes and and buildings and crops and things, then the impervious areas can be a problem because they generate more runoff and it has no place to go and causes a flash flood. So the two runoff mechanisms that I'm going to talk about, this is how hydrologists understand the conversion of rainfall to runoff. So we produce in the atmosphere some amount of precipitation. And then what happens? What happens is one of two things. Either the rate of rainfall exceeds the infiltration capacity of the soil, and whatever that excess is runs off. Or if we have saturated areas in the landscape, then any rain that falls on that saturated area has nowhere to go, so it can also produce runoff. And in the Northeast, saturation excess has been shown to be the most common runoff mechanism because our soils have a high enough infiltration capacity relative to the rainfall intensity that generally, usually, saturation excess is the mechanism that causes the runoff that makes streams run a little higher than they used to. But we'll see flash floods are a special case, and generally we think of them as extreme events. But I'll also talk a little bit about that, that concept of extreme too. Okay, so all of the landscape variables that contribute to those two types of runoff are highly variable throughout the Northeast. So we can see a range of saturated hydraulic conductivity, which I'm using as a proxy for infiltration rate. That ranges by an order of magnitude. The depth of the soil, so the depth either to bedrock or a restrictive layer or a permanent water table, ranges quite a bit from almost nothing to 1.5 meters. And then the slopes in this area, we have coastal plains that are basically zero slope. And then we have places in Pennsylvania and New York that are basically cliffs. And if you've ever driven in Pennsylvania, you know that the slopes in Pennsylvania are quite significant. And then you can see also a great deal of variation in impervious areas, and you can tell just by looking at this where the people are. You can also see that contrary to what an Alaska girl thinks of the Northeast as being all super populated, we actually have quite a few areas in this region that don't have people in them really very much at all. Okay, so that's variation in the landscape. Some landscape variables also vary in time as well as space, and this is a picture of the soil moisture product that I used. So you can see the variability throughout the region, but then also the difference between what May typically looks like in terms of soil moisture, what August typically looks like, a little drier everywhere. So we've got time variance as well as space variance. And then in the atmosphere, we have both space and time variability. Everybody likes to look at radar loops, so we're going to go through. This is one of the flash floods that was in my study. So you can see that over time we have a different. So the color ramp is radar reflectivity, which is related to precipitation. So you can think of more red and purple colors as intense precipitation and more blue and green colors as less intense precipitation. So the white dot here is where the flash flood happened. So over the course of a couple of hours, that dot goes from having basically no precipitation to very intense precipitation to no precipitation again. And here's a snapshot of what the intensity looked like at one particular time, 4 p.m. Eastern. This outline is the watershed that contributed to the flash flood. And you can see that parts of the watershed had no rainfall at that time, and parts had very intense 100 millimeters per hour rainfall. So lots of variability in space and time, multiple variables that we're studying. So it's a really complicated system that I'm trying to pin down here. So my research questions, the ones that I'm going to discuss today, what is the dominant mechanism of runoff contributing to flash floods in the Northeast? And then I'm also going to address how human infrastructure affects flash floods in this region. So my data set consisted of 180 flash flood events around the Northeast US. We chose them from the NCDC Storm Events Database. Like I said, we don't have a lot of remotely sensed data or instrument sensed data, so we have to go with what people reported and entered into this database. We looked at the years 2003 through 2007. We stuck with the warm season, so we don't have to deal with snow melt, which anyone who's ever done any hydrology knows snow melt is very difficult. We also avoided tropical storms because they behave differently in the atmosphere. And then once we figured out where these flash floods happened, we defined a watershed for each flood location, so the contributing area to that flood. And then within that watershed, determined the storm and watershed properties that I just talked about. So just a quick word, this is something that comes up a lot. People say, why don't you just look at where floods happened at USGS gauges, because then you have more information. You know the flow rate, you know the duration of the flood. But flash floods happen on a not only faster, but also a smaller scale than USGS gauges. So this is an example, again, of a flood from my data set, where the flood happened in this little watershed here. So we know that there was a street here that was flooded, and this is the contributing area to that street flood. The nearest gauge is here. So any flooding that might have happened may or may not actually show up in the hydrograph here at the gauge. So overall, in our data set, this histogram shows the watershed area. For the dark bars are our data set. The light bars are the USGS gauges around the active USGS gauges around the Northeast. So the average watershed size for our data set is about 75 square kilometers, and the average for the USGS gauges is about 1,000. So we're talking about a very different spatial scale here. Similarly with remote sensing, remote sensing has gotten very good at helping us understand where river floods are happening, the degree of inundation and the time frame. But again, the time and space resolution of these products isn't good enough really for us to identify where flash floods happen, how long they last, things like that. So here's a little tour of the NCDC Storm Events Database. That's a tiny bit blurry, but so the database, you can query it for a location, a date, and then the kind of events that you want to look for. So I filter by flash floods, and in this example, this is Tompkins County and 2006 to 2014. And what you get is a list of the flash floods that occurred during that time period in that place. And you can see that on some days there were more than one flood reported. So in our data set, we only considered one flood per day. So if there was more than one flood, we took the worst flood, the one with the highest precipitation depth. So when you get into the results of this database, you see time and place, and sometimes you get there's a narrative field where the person taking the report can give you more information, and sometimes the information is not very descriptive. It just says ditches overflowed. But sometimes they give you an actual pinpoint location. And this is really helpful for me as a hydrologist because I know for sure what watershed or contributing area was responsible or contributing to that flood. So we like those. Those are the best ones. So here's a map of our 180 events, and you can see some clustering of events in places like western Pennsylvania, down here in the sort of very populated area around New York City, and some places where we don't see flash floods, like the Adirondacks and north central Pennsylvania. All right, so once we establish where the flood happened, and like I said, if I can, I pick a location that's an intersection or a stream crossing or something like that as my outlet for my watershed. If I can't do that, then I take previously defined basins. So they're already delineated by the National Weather Service, and whichever basin got the most rain, that's the one that I consider as the contributing watershed for the flood. So then I used ArcGIS hydrology tools and a 10-meter DEM to delineate the watershed that contributes to each flood. And if you're familiar with flow accumulation algorithms, then you might be interested to know that ArcGIS uses an 8-direction algorithm. So it assumes that waterfalls, it can flow in it can flow like in basically the compass directions. Okay, so for soil properties, I used mostly the Surgo soil database. So I got porosity calculated based on bulk density, the saturated hydraulic conductivity, and all of these soil properties were averaged over the watershed. And then for soil moisture, I used a land surface model that accounts for precipitation, evaporation, soil properties, transpiration, and then models what the soil moisture would be on a given day for a 4-kilometer grid. And I used the top 10 centimeters. We consider that sort of the most hydrologically active area. For the atmosphere, the storm properties, we used a radar product that aggregates rainfall data into these polygons they're hydrologic polygons. So they're based on actual land surface, the elevation. And we were able to extract the intensity. So for my purposes, I counted the maximum 5-minute rain rate anywhere in the watershed. So even if it rained, with looking over that spatial and temporal variability, whatever the most intense rainfall was, that's the one that I considered. And then similarly, wherever in the watershed there was the most accumulation of precipitation, so a depth, we talk about precipitation in inches or millimeters, wherever that was the highest, that was what I considered the amount of precipitation for that flood event. And it's worth noting that as an exercise, I did do a more detailed temporal and spatial analysis or model of the 2 different runoff types. So for infiltration excess, I used the Green and Ampt equations and said for every 10-meter square, every 10-meter grid cell in a raster, what was the sum of the excess rainfall over the infiltration capacity summed up over the whole storm, and what would be the total infiltration excess runoff from that calculation. And for saturation, I used a model based on the curve number to say the same thing. For every 10-meter cell for the whole watershed, what was the sum of the saturation excess runoff based on soil moisture storage and the rainfall depth. This took me a couple of months to get all of the products, all of the inputs together for this one watershed. So I needed a method that was less computationally and sort of my time intensive to talk about the different runoff mechanisms in the flash floods in our 180 flood data set. So I came up with these indices where basically for infiltration excess, I said if the maximum rainfall rate anywhere in the watershed exceeds the average KSAT, then saturated hydraulic conductivity, then we're going to call that the rate ratio, so the excess of rain rate over soil infiltration capacity, which I know saturated hydraulic conductivity does not equal soil infiltration capacity, but I'm using it as a proxy. Similarly, if the rainfall depth exceeds the soil moisture deficit, that's going to be our depth ratio, so the rain depth over the soil moisture deficit. And I calculated the soil moisture deficit as the soil moisture the day before the event, subtracted from the total soil porosity, and then times the depth of the soil to bedrock or permanent water table. So the results of these analyses, you can see the variability in the landscape. These histograms are my data set. So before I showed you a map of the whole Northeast, this is what my data set looks like. So the impervious area was generally less than 10%. Slope was pretty variable, but around 10% was the sort of typical value. Saturated hydraulic conductivity, typically right around between 50 and 100 millimeters per hour, and soil depth right around a meter, typically. But some variation in those, and then also quite a bit of variation in the storm properties. So again, this is the maximum rate and the maximum depth for the storm, and you can see that most of the storms were pretty intense, 100 millimeters an hour. But lots of them were not very intense. So that's something to keep in mind as we talk about what's causing flash floods in this region. And I wanted to sort of point out for reference the storms in Ithaca. So every year we would expect to see a storm that's around 85 millimeters per hour at some point in the storm, and a total daily accumulation of about 50 millimeters. So that's normal for a year. So just to give you a reference of where these storms fall with respect to a normal year. So when I looked at the rain ratio, the rate ratio and the depth ratio, I came up with these quadrants. So basically, if the rate ratio is greater than 1, I would expect to see some infiltration excess runoff. And if the depth ratio was greater than 1, I would expect to see some saturation excess runoff. And then we have these other quadrants where maybe both runoff mechanisms are happening. And then this is a very interesting quadrant because we can't identify either mechanism happening by my methods. But I have some ideas about why things might be flooding down in that quadrant. So this is how it breaks down. About half of the events were infiltration excess, and 37% can't identify, and 3% saturation excess, 13% both mechanisms are happening. So the spatial distribution of these mechanisms or combinations of mechanisms, you can see sort of a spread of the mechanisms throughout the region, but then we have these clusters. And I think these clusters are important, and I'll talk about that more just in terms of figuring out why flash floods are happening. If, for example, in this area, if we're seeing both infiltration excess and saturation excess, then we know that this is an especially vulnerable area. And just the number of events that are happening in Western Pennsylvania also suggests that it's vulnerable, but why? That's the sort of question that I'm trying to get at here. So why are we having these events here that have neither especially high rate ratios or especially high depth ratios? What's going on? Why is it flooding here? And then in eastern PA and New Jersey, we're seeing a cluster of events that happen because of infiltration excess. So we can look at these variables again and look at the clusters and sort of start to develop some hypotheses about why we're seeing what we're seeing. So for example, some of the shallowest soils in the Northeast are happening in this northwestern Pennsylvania area. So it would make sense, given my assertions here about mechanisms, that saturation excess would be a likely mechanism here. They're not especially high hydraulic conductivities, so seeing intense rainfall and infiltration excess runoff is not maybe too surprising. In the cluster here of infiltration excess, we have a lot of people living here, so maybe the flash floods are happening largely because of impervious area and infrastructure, but maybe it's because the saturated hydraulic conductivity is a little low. I don't know. This one is an area where I think there's still a lot of room for more research, just in terms of, like I said, developing some hypotheses based on this structure of runoff mechanisms, and then testing them with models or with spatial statistics. Okay, so we looked at those histograms of the rate and depth of the storms in this data set, and I was struck by the fact that many of the events were not especially intense, and many of the events were not especially high in total precipitation depth. So I looked at the return period, or the recurrence interval, of the storms that caused these floods, and it turns out that half or more of the events are actually quite common. So for the accumulation or the depth, half of them are at least as frequent as the 5-year storm, and more than half in terms of rate, so the intensity of the storm, more than half of the storms were at least as frequent as the 5-year storm. So we're seeing flash floods happening because of events that are fairly common. So we think of flash floods as an extreme event, but they're actually not that unusual in terms of the probability or the frequency of the storm that's causing them. So what's going on? Why are we seeing so many flash floods in places where these storms are not especially uncommon? I think a lot of it has to do with us. I think a lot of it has to do with the infrastructure that we've built. So my little joke it's not even a very good joke, but if a flood happens when there's no one around, was it a flood? So we really only care about flash floods when they affect us, when they flood our property, when they hurt people. And so there's this bias toward flash floods that happen in places where people live, places where people have paved things and probably developed some stormwater infrastructure of some kind to deal with excess water. If we carefully design our stormwater systems, then this could help mitigate flash floods. That's what they're for, is to get the water off the road, to get the water off the parking lot or the places that it's not supposed to be. Unfortunately, that doesn't always work so well. So what do? We pave things, we dig ditches, we build culverts and municipal stormwater systems. And one of my research projects was looking deeper into one aspect of this infrastructure, which is road culverts. And I looked at a whole bunch of culverts in several watersheds in the Hudson River Valley. And I said, what's the capacity of this culvert? How much water can this culvert handle at its maximum flow rate? And then what storm would produce that much rainfall to max out that culvert's capacity?
What's a culvert?
It's a barrel, like metal or plastic barrel, that goes under the road. So you have a ditch, an open ditch, and then a pipe, and then an open ditch on the other side. So it's like, so it serves to get the water under the road, and then it's an open ditch on the other side. So in a city, everything would be underground. But in more rural areas, we just have these open ditches, and then the culvert gets the water under the road. Okay. So we looked at the capacity of these culverts, how much water can it convey at its maximum, and then which storm return period would meet or exceed that capacity. And then I color-coded them because people like to see simple ways of visualizing the results of this. So I actually gave these maps to the cities or towns that were in or close to these watersheds. And I said, these dark red culverts are your problem areas. These are the ones that are going to flood the most frequently. And you can see from this map that quite a few of them are in the orange and red range, which means that they're likely to be inundated or exceeded every 1 or 2 years. So that sounds like a lot. It seems like a lot of failure. And it turns out that this is actually verified by the people who live there. They say, yeah, this culvert backs up, floods the road every year or every other year. So it seems kind of extreme, but it's true in some places anyway, that these culverts aren't actually designed for the amount of runoff that's reaching them. And we don't have good records of every time this culvert floods because people only report it if it's extreme or if they notice or if they care. So I know here in the Ithaca area, I talk to people from Lansing who say their driveway floods every year or 2 years, or the ditch fills up and almost hits the road every year or 2 years. So we're kind of right on the cusp of infrastructure failures really frequently and in a lot of different places. So what can we do about it? We can, first of all, we can get people to report these floods or culvert failures more frequently. And that would maybe look like smartphone pictures uploaded and sent to the National Weather Service. They'd be geotagged so that we'd know exactly where it was. It could be more like an app where people can, put in their intersection where they are and say, there was a flood here on this day at this time. And if we had more detailed information about this is my sort of engineering, remotely calculated way of saying which culverts are vulnerable. But if we could have actual records of which culverts are flooding, that would be even better. And then we could give that information to the city planners, and they could decide if they have a little money, which they usually don't. But let's say they get some, they can prioritize which culverts to repair or upgrade. So I guess the bad news is that it's not going to get any better. So we're expecting more intense rainfall in the Northeast and in a lot of places in the world, and rare storms. So I already said that these flash floods are happening because of not very rare storms, but rare storms are becoming less rare. So we're going to see even more flash floods if my assessments of why these things are happening are true. And we're seeing that in a lot of places our infrastructure is not adequate, and it's going to be even worse as we get more and more rainfall, either more intense or more total accumulation. So maybe that leads to more floods. Yeah. So what does all this wrap up to mean? Basically, I think that I found evidence for both runoff mechanisms, infiltration excess and saturation excess. Infiltration excess seems to happen more often in the Northeast for flash floods. Regular storms, I think we can still argue that saturation excess is the dominant mechanism, but these are special. Flash floods are special. And so high intensity rainfall or high accumulation can cause flash floods depending on the landscape. So it depends on the soil, depends on the impervious areas. And we can see that not all flash floods require especially intense or especially high accumulation rainfall, which is important because a lot of research into flash floods is looking at these intense storms. And I'm saying that we need to be looking at the landscape too, and look at places that are vulnerable due to soil properties, due to slopes and impervious areas. And if we consider all of these landscape properties while we're talking about vulnerable areas, then and also find a way to talk about this time and space variable soil moisture, which is difficult, but find a way to incorporate that into our assessments of the susceptibility of any given watershed, then we're going to be better prepared to forecast when and where flash floods are going to happen. And then I found that runoff types are spatially clustered. And of course, where we build stormwater infrastructure, how well we design it matters a lot. It depends, it affects a lot when and where flash floods are going to happen. So research that still needs to happen. I think, like I said, the clustering of these runoff types is provocative, and I think a lot of work could still be done on figuring out what the causes are, why these runoff types are clustering in geographic areas. And then this can help us get to, is a particular area more susceptible to high intensity rainfall or high depth, or maybe it's susceptible to both, or maybe we need to start looking at reasons why small, not very rare storms are causing flash floods in a given area. And then I think it would be interesting to do more in-depth case studies like the one that I did at the 10-meter resolution, just to get an idea of any given watershed. You could say, this watershed is more likely to have infiltration excess or saturation excess runoff. And again, the more we understand what's going on in the landscape, the better we can prepare for the which storms are going to be likely to cause flash floods in that area. So thanks to my collaborators Todd Walter, Steve Clucci, and Steve Jessup, and funding from the NSF. And thank you for listening to me, and I have time for questions.
This has been a production of Cornell University, on the web at cornell.edu.